We are at the beginning of chapter 6 on triple integrals. We're going to do section 6.1, the definition of the triple integral. The goal of this section is to define the triple integral over a box and to use iterated integrals to calculate it. Now, we spent quite a bit of time looking at double Riemann sums and the definition of the double integral in the last chapter. We're going to go through the definition of the triple integral a little more quickly because it's directly analogous to the definition we've seen before. So, definition 6.1.1, a box B, which is AB times CD times RS in R3, is the set of all points R, x, y, z in R3, such that A is less than or equal to X is less than or equal to B, C is less than or equal to Y is less than or equal to D, and R is less than or equal to Z is less than or equal to S. So just a little remark, a box is the 3D equivalent of a rectangle that we used in 2 dimensions for double Riemann sums. So a definition 6.1.2, a triple Riemann sum for a function f of x, y, z over a box B, which is AB times CD times RS, AB times CD times RS, I said that right, with n subdivisions in x, m subdivisions in y, and l subdivisions in z is the Riemann sum Rnml is a triple sum. So it's a sum from I is equal to 1 to n of a sum from j is equal to 1 to m. The sum from k is equal to 1 to l of f of x, I, j, k star, y, I, j, k star, z, I, j, k star, delta x, delta y, delta z. So they are building up in complexity, our Riemann sums, but they are basically the same shape over and over and over again. Delta x is b minus a over n. Delta y is d minus c over m. And delta z is s minus r over how many divisions? L. And this monster, x I j k star, y I j k star, and z I j k star, we've seen this concept before. It is a sample point within the I j kth sub-box. So what is that? Well, let's take a look here. So this drawing, if we have a box, so in the x direction, this would be from A to B in the x direction, in the y direction from C to D, and in the z direction from R to S. So there's our box. Now we want to chop this up into subdivisions in x, in y, and in z. So if we take a subdivision in x, just a subdivision in x, well, we get a big old slab. And if we take a subdivision in, well, this one has a subdivision in z along with x, well, then we get a bar. And if we go ahead and also add a subdivision in y, well, that bar gets split up into a sub-box. So what do we see here? This dimension would be delta x. This dimension would be delta y, and this dimension would be delta z. And so that means here that our delta x, delta y, delta z up in the Riemann sum, that can be thought of as the volume of a sub-box. So that's what that can be interpreted as. Now what about this thing here, this sample point, right? X, I, j, k star, y, I, j, k star, z, I, j, k star. Well, that is a point within that box. So some point there would be x, I, j, k star, and so on and so forth, right? So just like in previous examples of Riemann sums, you're assuming that the function is constant over that box. And if we interpret f as density, right? So if f was density, if it was a density function, then that would be sort of like in, for example, grams per centimeter cubed. And if our volume was, well, maybe centimeters cubed, for example, if your density, right, F times the volume cancels out, and you're left with this product here, F at the sample point times the delta X, delta Y, delta Z. That would be approximately the mass of the sub-box. That's one interpretation, sub-box. And then, of course, that's a single sub-box. You need to add up all the sub-boxes in that bar. You need to add up all the bars in that slab, and you need to add up all the slabs in that box. Adding those all up is what those triple sums are doing. And so under this interpretation, this Riemann sum then becomes, if F is the density and the delta X, delta Y, delta Z is the volume of a subbox, adding up all those masses gives you approximately the total mass of the box. Now that's one interpretation. That's one way of getting our head around what an expression like this means. Definition 6.1.3, therefore, the triple integral of a function over this box is, well, you guessed it, we don't want the approximate mass, we want the exact mass, if indeed mass is our interpretation. So we are going to take the limit as the number of subdivisions, so as n, m, and l go to infinity of this beast up here. So of the triple sum, so I is 1 to n, j is 1 to m, k is 1 to what? To L? I keep forgetting L. Of x, I, j, k star. It takes longer to write this than it really does to understand what's going on. I, j, k star, delta x, delta y, delta z. That's not a z. And of course there is the qualifier that this definition is valid whenever this limit exists. So just a couple remarks which write down some of the comments that I scribbled up above. The first actually is about this dv. dv is the differential, and dv replaces, in the Riemann sum notation, it replaces the delta x, delta y, and delta z, and can be thought of as an infinitesimal amount of, well, we just said that that was volume, V for volume, an infinitesimal amount of volume. And compare when we did the double integrals with dA, which was an infinitesimal amount of area. What we had just said above, one of the more natural interpretations of the triple integral is one that we've looked at previously as well. So if f of x, y, z is interpreted as a density function, in fact, whether it's probability or mass density, doesn't matter, at each point of the box, then the triple integral represents the total volume of the box. And actually, if this were a probability density function, if f of x, y, z was probability density, then the triple integral would represent the total probability over the box. In the next video, we're going to jump right into integrating with Fubini's theorem for triple integrals, where we'll be able to evaluate these with iterated integrals. See you in a bit.